Hello students, I am Jisha Jose, Assistant Professor in the Computer Science Department of Rajagiri School of Engineering and Technology. In this presentation, we will be dealing with some of the topics from the course Principles of Information Security, which is included in the KTU curriculum of 8th semester Computer Science BTech. In this presentation, we will be dealing with the fifth module topics wireless LAN security. The usage of wireless networks have increased very much nowadays, and hence the security concerns that are involved are also increasing day by day. The prime reason for security concerns here being the very open nature of these networks. It is very easy to sniff out packets or inject malicious packets into such kind of networks. And due to all these reasons, carefully designed security techniques and protocols are needed to be implemented in these kind of wireless networks. Before going into the security protocols, let's cover and do some background study. When we talk about wireless LANs, the standard for referring to these wireless LANs are IEEE 802.11, or they are popularly known as Wi-Fi networks. And the basic building block that is used in such kind of networks is BSS, or Basic Service Set. A small diagram of the same has been shown in this slide. And every basic service set consists of two main components, an access point or AP and the wireless stations. The wireless stations can be laptops, computers, or any other such device which are connected to the internet or to the wired network through a common point known as the access point. Every wireless station and access point involved in a base service set will have a unique MAC address, which is a 48-bit address, and also every access point has got an SSID or a service set ID, which is basically 32 characters in length. Every access point will also have a channel number. An example of the same is shown in the diagram here. It is a wireless settings of a laptop that has been shown, where we can see the SSID given as NG Wi-Fi, the wireless on or off status is off, and the various other properties involved for that corresponding device. A collection of basic service sets is called an ESS, or an extended service set. As you can see in this diagram, here we have got two BSS which are connected to the wired network through their two access points. Two types of wireless LAN networks are possible. It can either be working in an infrastructure mode or it can be working in an ad hoc mode. From the diagram itself, we can understand the difference. In infrastructure mode, the BSS involved should have a common access point, whereas in the case of an ad hoc mode, there will be no need of any access points. Instead, they form a peer-to-peer network where devices communicate directly with each other. In infrastructure mode, the devices cannot communicate directly with each other. Instead, every communications will happen through the common access points inside each BSS. In almost all the organizations, there will be a wired network in place, which will be basically an Ethernet LAN connection. And in such kind of Ethernet LAN connections, an existing security infrastructure will already be present, which involves many kinds of servers like an authentication server for performing all the authentication tasks. Then there will be a remote authentication dial-in user service or a radius server which provides authentication, authorization and accounting activities for users who are connecting to the network. The main challenge that is involved here now is to develop protocols which can integrate the wireless LAN with the security infrastructures which are already available for the wired networks. Whenever a wireless station is up and active, the first and foremost step it has to do is to discover an access point. And this process is known as scanning. Scanning can be done in two ways. active scanning as well as passive scanning. In the active scanning method, the wireless station will send out probe request packets to the various access points around. Whichever access point responds with a probe response packet first to that access point, our device can connect. Whereas in passive scanning, the wireless station will wait for beacon frames that have been periodically transmitted out of access points, and whichever access point is near or whichever access point can send out a strong beacon frame, based on that, the client will connect to the corresponding access point. So after the scanning step, the next step is the association step. To become a part of the wireless LAN, the station will need to associate itself with the access point. And the procedure followed is the client, after performing an active or passive scan, the next step will be the client will send an association request to the access point. After receiving this request, the access point will respond with an association response, which includes the association's ID. And once the association response is received by the client, the connection has been established between client and AP, and now both of them can communicate with each other by sending data through the wireless means. Now we will go into detail about how to implement security in wireless LAN networks. Authentication and other security functionalities that have been used in wireless LAN have evolved over years. Various techniques have been used, and depending on the disadvantages and advantages of each method, new technologies have been introduced. Some of the commonly used technologies include WEP or Wired Equivalent Privacy, WPA or Wi-Fi Protected Access, and WPA version 2. Before moving into the wired equivalent privacy method in detail, we shall first see what was done before that. That is how authentication was achieved before WEP. It was done using two things, either by using the SSIDs of a station or by using the MAC address of a station. And it was found that both these methods are not secure. That is, in the first case, if you simply knew what is the SSID of a station, it could authenticate itself to an AP. But what's the problem here? An attacker can easily sniff out SSIDs from beacon frames and can impersonate themselves and gain access to an access point. The second method was using MAC addresses. In the case of MAC addressing also, attackers could do MAC spoofing. So both these methods were found to be not secure. Since we have already seen the disadvantages of the authentication procedure followed before introducing the WEP protocol, now we will see how authentication can be done using the wired equivalent privacy protocol or the WEP protocol. The main algorithm that is followed here is called the challenge response protocol, using which stations can authenticate themselves to the access points. So here what happens is, initially in the first step, an access point will generate a challenge value, and this challenge value will be sent to the station who wants to authenticate itself, and the station who wants to authenticate will encrypt that challenge value and will send it back to the access point. And to perform this encryption, the RC4 encryption algorithm is used. You have already studied RC4 encryption algorithm in your previous semesters. It is a symmetric encryption algorithm. Here what happens is, the station will compute a key stream value, which is actually a function of a 40-bit shared secret value S, which is common to all the wireless stations which are present in the current BSS, and also there will be a 24-bit initialization vector. Using this shared secret value S and the 24-bit initialization vector IV, a key stream value is computed, and this key stream value will be XORed with the challenge value which has been just received from the access points, and this will be the value that is sent back as the response to the access point, and the response along with the initialization vector will be send back to the access point. And the access point, what will happen, this response and IV value have to be decrypted. To decrypt it, since it is an XOR operation, you can easily generate the key stream value again at the access point using the shared secret value available at the access point, and the IV just received, the key stream value will be generated, and this key stream value will be XORed with the current response value that has been received from the station. And if you get back the challenge value which was initially sent from the access point to the stations, then we can say that the verification procedure is completed, authentication procedure is completed, and the wireless station has been successfully authenticated to the access point. And this shared secret value S will be common to all the stations who are trying to authenticate to a common access point. And this protocol is known as the challenge response protocol. Even the challenge response protocol that was introduced had its own disadvantages. There were different kinds of attacks possible, like, for example, attackers can monitor the challenge response pairs that are being sent between wireless stations and access points. And by monitoring this pair, they could actually compute the key stream that is being exchanged between the access point and the wireless stations. And once they can compute the key stream, an attacker can also authenticate himself to an access point by using the obtained challenge value and the computed key stream. And the access point will have no idea whether that station who's trying to authenticate himself to the access point is an attacker or a genuine wireless station. Another possibility is a case of a dictionary attack to find out what is the different possible values of the shared secret value S, which is actually supposed to be known only to the wireless stations. Now that is also possible. And also, the third disadvantage over here is there is no support for authenticating an access point to a station. That is, there is only a one-way authentication happening from a station to an access point. Even if an attacker is behaving as an access point, and if some random stations are trying to authenticate to the attacker thinking that he is a genuine access point, that also cannot be identified. That is, rogue access points can masquerade themselves as authentic, and they can try to get access to different wireless stations. So all these are the different disadvantages for the WEP protocol, and due to the same reason, more and better protocols were introduced for security in wireless LAN networks. The next security protocol that was introduced in wireless networks was WPA, or Wi-Fi Protected Access Protocol. Here, this method was developed by the Wi-Fi Alliance, and the main aim was to provide sophisticated data encryption and better user authentication techniques compared to the WEP protocol. And in 2004, this method was standardized by IEEE as 802.11i, and it was designed to be backward compatible with the WEP protocol so that this method can be easily installed and adopted by the already existing wireless networks. And this WPA protocol was supported on most of the WEP based devices with a simple firmware update. And the two main discrete modes of working of this WPA protocol was the enterprise user mode and the personal user mode. That is, we could use this particular security architecture in enterprise networks as well as in personal wireless networks. When it is used in enterprise networks, it was called the WPA EAP protocol, and it provided the extensible authentication protocol techniques. And when it was used in personal user networks, it was called WPA PSK, where pre-shared keys were used for simple implementation and management among home users or small offices. So this is what is known as the Wi-Fi protected access method, or the WPA method. It was found to be better compared to the previous method, that is the WEP protocol, or wired equivalent privacy protocol. As mentioned in the previous slide, the WPA protocol was standardized by IEEE as IEEE 802.11i. And in this particular method, the encryption technique that was used was called TKIP, or Temporal Key Integrity Protocol. And this IEEE 802.11i is actually an IEEE 802.11 amendment which was used to facilitate secure end-to-end communication for wireless networks. And the main aim of this method was to improve the mechanisms for wireless authentication, encryption, key management, and provide detailed security compared to the previously existed WEP protocol. And this protocol was also known as IEEE 802.11i 2004. And after the WPA protocol, a second version of this same protocol was introduced, which was known as WPA2. And the basic difference between WPA and WPA2 was in the encryption method that was used. In WPA, the encryption method was TKIP, and in WPA2, which is an enhanced version, the encryption method that was used was AES, or Advanced Encryption Standard Algorithm. And this IEEE 802.11i and the WPA2, the enhanced version, they together formed a complete wireless security protocol. So these are some of the currently used wireless security protocols in wireless LAN networks. Next, we need to see how authentication is done in this standard IEEE 802.11i protocol, or the WPA protocol. It uses IEEE 802.1x, that is a protocol which supports authentication at the link layer. And three basic entities are involved here. The three basic entities are the supplicant, or the wireless station himself, the authenticator, or that is the access point, and the authentication server, which will basically be a radius server. And the main framework that is used here for providing authentication is the EAP framework for providing authentication protocols. So this is how authentication is done in this IEEE 802.11i network. As I mentioned in the previous slide, the authentication mechanism performed in the WPA protocol, or in the standard IEEE 802.11i protocol, is based on a framework called the EAP framework, or Extensible Authentication Protocol framework. It is a framework that can be used for performing security in wireless networks and point-to-point connections. Various authentication protocols can be supported using this framework, and the main feature of this framework is that it works on the basis of some request messages and response messages. Different methods have been devised using this corresponding framework. Around 40 of them are available, but in our syllabus or in our particular curriculum we will be dealing with 3 or 4 protocols from this corresponding framework. Okay, so this is what is known as EAP, or Extensible Authentication Protocol. It's just a framework using which you can develop different methods for providing security in the IEEE 802.11i method of wireless station security. This is the working model of the EAP framework, the basic working model. Here what happens is a user or a wireless station will request a connection to a wireless network through an access point. So some authentication mechanism is to be performed, and for this what the access point will do is it will first request an identification or an ID data from the wireless station or the user, and that data will be transmitted to an authentication server. The usually used authentication server in wireless networks is the radius server. Okay, and the authentication server, what he will do is he will ask the access point for proof of the validity of the ID that has been just submitted by the AP to the radius server. And once the access point obtains verification from the user, or the proof for the ID that has been submitted, and that value will also, the proof value will also be sent to the authentication server, and after clear verification procedures are carried out, the user or the wireless station will be allowed to connect to the wireless network as requested. This is the basic working model of an EAP framework. Based on this working model, different methods have been developed under the EAP framework for performing security in wireless networks. This is a diagrammatic representation of whatever we discussed right now. Here we have the three components, that is the wireless station, the access point, and the authentication server or the radius server. Now when a station wants to authenticate himself to an access point, first the station will request for authentication, and what the AP will do is he will request for the identification data of the station. That is the first step. Identity request is submitted to the station. The station will respond with his unique ID. It can be any value which is unique to the station. And what the AP will do is the AP will send this ID value to the radius server as a radius access request. And once the identification value is received at the radius server will ask for proof of this ID value to the access point. That is the radius access challenge that is sent back to the AP. Once the AP receives the challenge, the AP will again communicate with the station for requesting for the proof of the ID that has been just submitted. That is what is known as the authentication request. And once the proof has been asked to the station will respond with an authentication response where he sends back a proof of the ID that has been already submitted to the AP. And this AP will forward that corresponding value to the radius server again as a radius access request. And if the authentication server or the radius server is satisfied with the proof and the ID that has been submitted initially, then the radius server will allow the connection to be forwarded or proceeded with, and he will respond back to the AP saying that he has accepted the corresponding ID and the proof of ID, and then the AP will communicate back to the station saying that the authentication procedure is successful. Now this is just a framework. Depending on the method that is developed using this corresponding framework, the data that is exchanged or the ID and the proof values that are exchanged between the station, AP and the authentication server can change, and this is what is known as the EAP protocol or extensible authentication protocol. Now we will see some of the authentication methods that are implemented using the EAP framework. First one is EAP based framework on MD5. In this method, the authentication server will challenge the wireless stations to transmit the MD5 hash of the wireless station's unique identification, say for example a password. Okay, the problem with this method is it is not secure because any attacker can eavesdrop or listen to the message exchanges taking place between the access point and wireless stations, and they can replay the hashed passwords to impersonate themselves. And also the second disadvantage is there is no authentication of the access points done to the station. Only stations are authenticating to the access point. Okay, and it also doesn't provide a means to derive any kind of dynamic or session keys. So all these are the disadvantages of this method based on MD5. Only one way authentication is done and easy eavesdropping of message exchanges is possible. No authentication of the access point to stations, or there is no use of any session keys involved. The second method is the EAP framework based method on TLS. TLS means transport layer security. So this method is based on the SSL or TLS protocol. It is the most secure method that has been developed using this EAP framework. Here, mutual authentication and agreement is done between the access point and wireless station. That is, both of them authenticate to each other, and this is done based on a master session key. And here, the access point and the wireless stations use digital certificates to perform these kind of mutual authentications. And the only issue that can arise in this particular method will be that the certificates that are used for performing mutual authentication must be managed on the client side and server side, that is on the wireless station side and the access point side, which can be one of the limitations of this method. So this method is called the EAP framework based method on TLS. In the previous method, that is the TLS based method, The only limitation was that the digital certificates had to be maintained at the wireless station side as well as the access point side. So to overcome that problem, we have the next method, which is called the EAP TTLS method, or tunneled TLS method. Here, certificates are needed to be maintained only at the access point end. And what the access point will do is it will first authenticate itself to a station, and then both sides will construct a secure tunnel between them. And using this virtual tunnel mechanism, the stations can now authenticate themselves to the access point, and the actual authentication is actually made to the radius server, and in fact that will confirm the authentication to the AP also. And once this mutual authentication is carried out, they can perform communication with each other. And the last method is the PEAP method, or protected EAP method. It is similar to the previous method, that is the TTLS based method. And here the secure tunnel is used to start a second EAP exchange where a station authenticates itself to the authentication server also. In the TTLS method, the stations were authenticating themselves to the AP, and in this method the stations will authenticate themselves to the authentication server. So these are the different four methods that have been proposed using the EAP framework. First one was EAP framework based method using MD5, then the EAP framework method using TLS, then we have the TTLS based method, and the last one was PEAP method, or protected EAP method. This table gives a comparison of the four methods that we have discussed just now, that is the EAP based framework method using MD5, using TLS, using TTLS, and using protected EAP. Okay, and the different methods have been compared based on various factors, like whether a client side certificate is required, a server side certificate is required, how the key management is done, whether there is any rogue access point detections done or not, who's the provider, then the authentication attributes used, whether it is one way or mutual, and the deployment difficulty, and finally the level of security that is achieved in the Wi-Fi network. Okay, so this is just a comparison of the four methods that we just discussed now. Almost 40 different methods are available under the EAP framework, but we have just discussed these four methods. So now we have completed the authentication procedures and methods involved for authenticating a wireless station to an access point. Next, we need to see how the keys are defined, or the keys are derived for performing security operations between the wireless stations and access point. That is, we need to see what is the key hierarchy. Before discussing the key hierarchy, we need to see what are the different kinds of keys that are used in the wireless systems. First one is called pairwise key. They are used for protecting traffic that is flowing between a station and an access point. Second one is group keys. They are used for protecting traffic that is broadcast or multicast between an access point and multiple stations. So there are two kinds of keys: pairwise keys and group keys. Now, how are these pairwise keys and group keys derived? It is based on a key hierarchy, and at the root of this key hierarchy we have a key called the PMK, or the pairwise master key. This PMK key can be derived using two methods. First one is the method where the station and an authentication server will agree upon a session key, and the session key is called an MSK, or master session key, during the authentication procedure itself, which we have already discussed, and this MSK will be sent to the access point. Now the station and the access point can use this MSK, the master session key, for deriving the pairwise master key. And once a pairwise master key is derived, from that key onwards we can derive out the sub keys which are required later. Second method is of using a pre-shared key or a PSK for each session of operation between the station and the access point, and this PSK will be different for each session, and from this PSK a PMK or the pairwise master key will be defined, and from that PMK onwards the later on required subkeys can be defined. So these are the two methods that can be used to derive a pairwise master key, and from this pairwise master key, which is behaving as the root of this key hierarchy, the different subkeys required can be derived. We have defined the pairwise master key at the root of the key hierarchy. Now we need to define the further subkeys. First one is pairwise transient key or PTK. It will actually be a pseudo-random function of different values like the PMK, two nonce values that are chosen by the access point and the station, and their corresponding MAC addresses. All these four values will be put together and combined using a function to form the pairwise transient key. Once we derive the pairwise transient key, we can derive three more subkeys, which are the temporal key, key confirmation key, and the key encryption key. Temporal key or TK will be used for encryption and integrity protection of the data that is flowing between access point and stations. Second one is the KCK or key confirmation key. It is used for integrity protection in the various four-way handshakes that are happening in the wireless network. And the last one is key encryption key or KEK, which is used for encrypting the messages containing group keys. So these are the different keys that are used in the security of wireless LAN networks. They may be used in various situations and operations depending on the requirement. So the different keys, where at the hierarchy we have the pairwise master key. From the pairwise master key we define the pairwise transient key. Then we derive three subkeys called the temporal key, key confirmation key, and the key encryption key. Suppose some communication is to happen between a wireless station and an access point, and if the security protocol used is WEP protocol, how the data is protected. That is, we need to see how secure communication happens between a wireless station and an access point. This is achieved using RC4 encryption in the WEP protocol. So as we discussed in our previous slides, in the RC4 encryption procedure, initially a pseudo-random key stream KS will be generated, which is actually a function of a static secret value S, which is commonly shared between all the communicating wireless stations, and also there will be a random per message initialization vector IV. The shared secret S value is of 40 bits and the initialization vector is of 24 bits. So total it will be a 64-bit key. Using this 64-bit key stream and the plain text which is to be communicated, we can calculate the ciphertext as C is equal to plain text XOR the key stream value. And once this ciphertext is calculated, the ciphertext and the initialization vector will be sent from the station to the access point. And at the access point, to decrypt the message, the receiver will regenerate the key stream using the initialization vector just received and the already available shared secret value S, and using this recalculated key stream and the just received ciphertext, it will again perform an XOR operation to retrieve back the plain text. So this is how data is protected during data transfer in the WEP protocol. The previously discussed data protection model, if it is used in the WEP protocol for data transfer between a wireless station and access point, different kinds of attacks are possible. We will discuss some of them. First one is known as the known plain text attack. It is basically an attack model for cryptanalysis where the attacker has got access to both the plain text as well as its encrypted versions. And the advantage of this attack is that it can be used to reveal secret keys and various code books. In this particular case, we have already assumed that the initialization vector is only 24 bits in length. So, For a given shared secret value S, only 2 raised to 24 distinct key streams are possible. Now assume that an attacker has got access to two frames which are encrypted using the same initialization vector IV. And also assume that the ciphertexts present in these two frames are C and C dash and the plain texts be P and P dash, where one of the plain text is known. This is what is known as known plain text attack. If this is the scenario, I can very easily find out the other plain text value P dash because the key stream is the same. It will work based on the simple property of XOR. XOR can be exchanged in between the equality symbols very efficiently. That is, since C, C dash and P are already known, to find P dash we can use the property of XOR that P XOR P dash will be equal to C XOR C dash, and from that we can easily rearrange the equation and find out P dash as P XOR C XOR C dash. Like that we can get access to the value of P dash or similarly any other kind of plain text. This kind of attack is known as known plain text attack. The next kind of attack is known as message modification attack. Here, the attacker wishes to modify the messages that are sent by a legitimate user or a wireless station. Suppose, for example, the wireless station who's sending the data, the data that has been sent, if it is represented as M1F, M2, where it is M1F and M2 represent some binary combination of strings, then what the attacker wishes to do is he tries to modify the message in such a way that he is going to substitute the binary string F with another string F dash, so that by the time the plain text reaches the receiver side and in an encrypted form, when it is decrypted, the message that is received at the receiver will be in the form M1 F dash M2. That is, the message is getting modified. The attacker doesn't want to access or understand what is M1 and M2. He simply wants to modify that F part into F dash part. This kind of an attack is known as message modification attack. So assuming that the initial plain text was M1FM2 and the modified plain text which needs to be M1F-M2, what the attacker is going to do is he will intercept the ciphertext that is coming from the sender and which is in the form M1FM2 concatenated with the cyclic redundancy check value of M1F2M2, which is the whole, and this full thing is XORed with the key stream. Suppose this is equation 1. Now what the attacker will do is he will intercept the ciphertext and he will generate a new string which actually is of this form, that is 0 raised to mod M1 concatenated with F XOR F dash, where F indicates the original binary string in the plain text which was sent. F dash is the modified message that the attacker wants to insert, and again concatenated with 0 raised to mod M2. Here 0 raised to mod M1 means it is actually a string of mod M1 zeros. Mod M1 means it is the length of the exact length of the message binary string M1. So that many number of zeros concatenated with the original F XOR F dash and then again concatenated with 0 mod M2. This kind of a new string is created. Now in the second step, a CRC of this modified string is generated, and in the third step the attacker will concatenate together this new string and the CRC of the new string, and then finally XOR it with equation 1, that is whatever ciphertext the attacker has intercepted from the message, this full ciphertext will be XORed with the new string that the attacker has created. And if you solve this equation 3, it is found that it will be of this form, that is M1 F-M2 concatenated with the CRC of M1 F-M2. That is, eventually what happens is the F value which was there in the original ciphertext which was sent from the sender that will be completely replaced with the f dash value. If you solve this equation 3 mathematically, you can prove it. And that is what is known as message modification attack. So like this, the user will be able to modify a part of the message, and the sender will never know that the part of the message has been modified, which the sender thought he had encrypted and sent to the receiver. And this kind of an attack is known as message modification attack. We discussed about the various attacks that are possible on the data that is being transferred between wireless stations and access points till now. That is, it can either be a known plain text attack, or there can be a message modification attack where some attack is done on the data that is being passed. Now there is also a situation where in wireless LANs, misbehaving nodes themselves can launch a variety of attacks. That is, the wireless stations themselves can be used as attacking senders for performing different kinds of attacks. One of them is known as the frame spoofing attack. It is an example of an active attack. Here what happens is, to understand frame spoofing in detail, we already know that all the 802.11 frames which are passed between wireless stations and access points, they contain the MAC address of the sender in the header part. And when we are performing encryption on the data that is passed, the encryption is done only on the payload part. There is no encryption done on these kind of values like the MAC addresses. And also there is no mechanism for verifying the correctness of the self-reported identity. That is, we don't have any mechanism to check whether the MAC address present inside the header of a frame is correct or not. So what happens is, as a consequence, an attacker can spoof or imitate some valid nodes, and they can create spoofed MAC addresses or any kind of masquerading operations they can do, and they can request for MAC-like services on their behalf. Okay, so there are two kinds of spoofing possible. You can either do spoofing of de-authentication frames, or you can either do spoofing of power management frames. So not only attack is possible on the data or the payload that is being passed between wireless stations and access points, you can also have attacking nodes or attacking stations present who can perform different kinds of spoofing on the frames that are being passed through the wireless stations and access points. So such kind of vulnerabilities are also possible in the WEP protocol. First one is spoofing of de-authentication frames, which is known as a de-authentication attack. We already know that a station has to do two things, that is authentication and association with an access point, before it can actually exchange data with the access point. And at any point of time, any wireless station can de-authenticate or de-associate itself from an access point by terminating the connection with that corresponding access point. This is usually done using a de-authentication frame. Now in a de-authentication attack, what happens is, an attacker can purposefully generate a spoofed de-authentication frame and send it to an access point with a spoofed MAC address or a spoofed sender address, saying that please de-authenticate or de-associate such and such wireless station from your connection. Now, but the actual wireless station will have no idea that such kind of a de-authentication frame has reached the access point. Such kind of an attack is known as de-authentication attack. For example, suppose an attacker is generating a de-authentication frame with a sender address equal to station underscore 27, which is actually the MAC address of some genuine wireless station. And actually this particular address has been spoofed by the attacker, and the receiver address will be set as the address of the access point. So what happens is, the access point, when he receives this de-authentication frame, he thinks that by looking at the MAC address, he understands that it is the address of the station underscore 27, and he will think that that corresponding station wants to terminate the connection, and the AP will terminate the connection, but the actual station underscore 27 will have no idea that the connection between himself and the access point has been terminated by someone else. Such kind of an attack is known as spoofing of de-authentication frames. This is a diagrammatic representation of the deauthentication attack. Initially, you can see that when a client wants to connect a client, for example a wireless station wants to connect with an access point, there are two steps involved, basically authentication and association. So after these two steps, the connection is established, and once a connection is established, they can exchange data with each other smoothly. Now an attacker who is sitting in between the wireless station and access point, what he will do is he will generate a spoofed deauthentication frame which will contain the sender address as the MAC address of this client and the receiver address as the MAC address or the address of the access point. And this deauthentication frame will be sent to the access point, and the access point will think that this particular station wants to actually de-authenticate and de-associate from this connection. So what happens is, in the future, when the actual wireless station is sending some data to the access point will say that you have already de-authenticated yourself from this connection, so I will not accept this data. So such kind of an attack is known as the de-authentication attack, using spoofing of de-authentication frames. What will be the major after effects here? That is, the actual station underscore 27, when he is trying to send the data to the corresponding access point, the access point will say that you have already de-authenticated and de-associated from the connection. So what will happen is the station will have to perform a time consuming re-authentication and re-association process to resume the connection with that corresponding access point. So time is getting wasted, and what the attackers can again do is that they will repeatedly keep on sending such kind of spoofed frames to the access points to slow down or prevent communication between various stations and access point. So this is the after effect of de-authentication attack. Next kind of attack that is possible is the spoofing of power management frames. We know that wireless stations are usually working on batteries, and to save power, they may periodically they may switch off their transceivers. Before switching off their transceivers, they will inform their corresponding access points that their corresponding station is going into a power saving mode, so that the access points, what they will do is they will buffer or collect together all the frames that are actually intended for that corresponding station, and when the station wakes up later, the station will inform the access point that it has come back to an active state by using a power save pole control frame. And once this power save pole control frame is received at the AP will deliver all the buffered or stored up packets which were intended for that station to that corresponding station. Now what kind of attack is possible over here? What the attackers can do is they will spoof up these kind of power save pole control frames, and they will try to cause some havoc in the interaction between the wireless stations and access points. Such kind of an attack is known as the power save pole attack. Here what happens is the access point will receive some spoofed up frames from the attackers, stating that such and such wireless station has come back to the active state and he wants his buffered frames. So what happens is the AP, who has no idea whether it is a spoofed frame or actual frame, he will start delivering the buffered packets to the actually sleeping station, and that sleeping station will have no idea about this spoofed frame. So what happens is the frames that are coming from the AP will not be captured because that corresponding wireless station is now in the sleeping mode or in the power saving mode. And when the station actually wakes up and comes to an active state and sends the genuine PS port control frame to the access point for getting his buffered frames, there will be no response from the AP because the AP has already emptied his buffer because of the arrival of that spoofed frame. So eventually what happens is all the actual frames that were meant for that wireless station have been lost. So such kind of an attack is known as the PS pole attack. This is a diagrammatic representation of the PS pole attack. Here we can see initially the client, or for example the wireless station, will connect himself with the access point using authentication and association procedures, and then suppose the wireless station wants to go into a sleeping mode, he will give a power saving request to the access point. Then there will be a power saving response, and the wireless station has gone into the sleeping mode. Now, what the attacker who's sitting in between the wireless station and the access point can do is he will send a spoofed PS pole control frame to the access point, and the access point who has already buffered and collected together data which has come from other clients and all, he will start sending it out because he thinks that this PS pole control frame has come from this wireless station. But what happens is this wireless station is still in the inactive mode, and this data will be lost. And the attacker, who is very brilliant, he will also send back an spoofed acknowledgement frame stating to the access point that he has received all the data which the access point has sent out, and the access point will have no idea what has happened. The wireless station will also have no idea what has happened, and finally the data is lost. And this is how a PS pole attack is done. So such kind of an attack is known as PS pole attack. With this, we come to the end of the first session on module 5, that is wireless LAN security. In this presentation, we discussed about the wireless LAN networks. We did a background study on what are the different types of wireless LAN networks, what are the different modes of working of wireless LANs. Then we saw the security architectures which have been implemented in such kind of networks, starting from the WEP protocol, the WPA protocol, and the WPA version 2 protocol. Then we saw the different kinds of vulnerabilities of the WEP protocol, the different kinds of attacks possible in WEP protocols, etc. And in the future presentations, we will be dealing with the security architectures that are implemented in cell phone networks. Thank you.